So if you want to get your slides up now, Andreas.
Okay, let's start it. We're going to start with my sharing my screen. So, okay, sharing.
Do you just want to
Is
introduce?
everything okay?
Yeah, we'll just give a few minutes for everybody to arrive, and then we can get some introductions. Andreas, if you press on the top left, there's a purple button that says Present in Teams.
Let me see, Present in Teams. So I need to. Which one?
On that screen you're presenting now, it's the third button from the left along the top panel.
From the left.
Mm-hmm.
This. Okay. This one. But it says try the new Teams.
I'll just leave it then.
Okay.
Should we give it till 4 minutes past? Yeah, and then we'll get going.
Yeah.
Sweet. Did that Q&A question come through for you, Haley and Hannah? I just put one in the Q&A box as a test.
Yep, I can see that.
Sweet.
Yep.
I think we're pretty much ready to get started whenever you're ready, Haley.
Cool. So this evening we're going to have 3 talks from some up-and-coming engineering geologists. Each talk's going to kind of last 10 to 15 minutes, and if you've got any questions during the talk, just pop them in the Q&A group and put a reference to which talk it was, so whether it was talk 1, talk 2 or talk 3. And then after the 3 talks we'll come back with the questions so that everybody has some similar amount of time. If everyone can make sure their microphones are off, and then if you want your video on, then leave it on. If not, turn it off. And that's pretty much all the admin bits. First of all, we've got Andreas. He is a research assistant and geotechnical engineering student at the University of Alberta. And his case study, as you can see, is going to be on investigating the progressive failure of slopes. So Andreas, if you want to start your presentation.
Okay, sure. Thank you for that presentation. I'm going to start sharing my screen. Is everything okay with that one?
Yeah, looks good to me.
Okay, let's start it. Okay. Good evening, everyone. For me, it's a pleasure to be here presenting results from my master's degree research, which is about a case study related with the progressive failure developing in slope stability problems in open pit mines in a porphyry deposit. So why is this important? This is important because the main goal of any open pit operation is to maximize the net profit. And this is usually achieved by using, from a geotechnical perspective, by applying optimization algorithms. And as a base for these optimization algorithms, we got the geological model, your geotechnical model that includes your parameters, your geotechnical parameters. So it is quite important to understand how the geological model complexity affects your numerical analysis. In order to understand the previous, but also how different excavation sequences can affect your numerical representation of the progressive failure and your slope stability problem, we selected a case study that it was a failure occurred in a deep open pit mine. And this failure occurred in the northeast wall, as you can see in the figure. And this failure, it wasn't a root. It was something that it was following a process. As you excavated the material following the northwest direction, the northeast wall presented deconfined, and as a product, it was the failure that you can see in the image. And because at the mine site, it was present a porphyry deposit. This is a schematic representation of a porphyry deposit. Sorry for the geologists present today, but I'm gonna make like a simplistic explanation of the porphyry deposit. But from engineering perspective, it is just lava or magma ascending through a host rock, and because of the high temperatures and the contact with the surrounding rock, it is produced different alterations. And depending on these alterations, this is gonna affect the strength properties of the rocks and rock masses.
Andrea, sorry to interrupt. I think you're just sharing the first screen at the moment. Is you okay just to either move to the next slide or swap the screens over?
Oh, really? Because I only have one screen.
Or whether you're sharing the wrong item, I'm not sure.
Let me see.
That's it. Now we can see. Cool.
Okay. And now you can see this one.
So we can see kind of like a cross section at the moment.
Okay, I'm gonna share the complete window.
Cool.
Let me see. I'm gonna stop sharing and then resharing screen window. Okay. Okay. Can you see this?
Yeah, now we can see that. Okay.
Perfect.
Yeah, I can see
Thank
that.
you. So I was explaining because of the geological environment was a porphyry deposit. This is a schematic representation. Basically, a porphyry deposit is created with lava and magma is ascending through a host rock. And because of the high temperature and the contact with the surrounding rock creates different alterations. And depending on these alterations, there's going to be different strength properties for the resulting rock mass. Now, more in detail, the case study geological setting presents lithologies like andesite, rhyolite that you can see on the left in this plan view, where is overimpose the model limits. And additionally, in the orange color, you can see the porphyry stock, which is basically granitic rocks, granodites, this kind of rocks, but also from the weakest to the strongest, you can see also the alterations. The weakest is the argillitic alteration, and the strongest is the potassic. These two cross profiles are important to understand which material is present in the fail zone, like in the cross profile A, where the most predominant material is the andesite, but also it is present sericitic chloride alteration. And it's important, this cross profile view, because of the elongated porphyry stock material. That is important to understand the failure mechanism. And the upper one, it is just to illustrate the excavation sequence that is called in this open pit mining world as pushback sequencing, which is basically the order of the blocks that are excavated. And most of the material excavated here is the porphyry stock. Along with the geological setting, it is also important to define some initial parameters, geotechnical parameters, like the presented on the left, which were obtained from literature review. These parameters were used in the geotechnical model that is presented in the upper right corner, which is basically a summary of the distribution of lithologies, alterations, but most important, it is the figure below that represent the actual slip surface that seems to be constrained by the elongated body, which is much stronger than the other materials. Now, related with the failure mechanism, as I say, the failure occurred in the northeast wall, as you can see in this figure, but connected to previously said, related to the elongated body that is underneath the slope surface. The slope surface resembles the one that you can see in translational movements. And when it was reviewed, the structural data, no kinematical possible case was configured. So we ended up in the conclusion that the slip surface was through breaking the rock mass. Now, for calibrating the model, it was used information from the mine operator, the red curve, but because wasn't completed, it wasn't enough to cover all the period, the movement period. It was necessary to complement, to include additional measurements from satellite images from Google Earth. And this is why you can see a blue line that covers completely the kinematic process of the movement. This history plot, it is for this prism or monitoring point that is at the middle of the failed surface. Now, because our interest is to study the relationship between the geological complexity models, geomaterial model, and additionally the excavation sequences in developing the progress failure. For the first part, it was created 9 different models, from linear elastic material models to the most advanced using the strain softening models. For the part of the geological model, the simplest one it was the homogeneous, and the most complex was incorporating lithology plus alteration. Then we built the geometry, the meshing process, and we did a back analysis process for each one in order to define which one represent much better the actual fail. Now, about some model's characteristics and assumption, it was done like a separation between the core, the fail zone that is presented on the left. But it was because we wanted to increase the discretization of the mesh that is so important in order to get good results. But also, we did simplification in the geometry of the excavation sequence, as you can see in the recording. As a result, it was possible to establish that by improving your geotechnical model, I mean by improving your geological model, your constitutive model, it was possible to reproduce the actual failure, which is represented by the red curve on the left with the blue dots. And we got the conclusion that this is the best fitting model, which correspond the one using lithology plus alterations and with the more Coulomb material and the strain softening. We got to the conclusion that it was the best because we compare their statistics related with the failure depth, superficial extension of the failure, and the involved volume with the real fail statistics, as you can see in these bar plots on the right. The second part. Now, this slide is for illustrating how by increasing your geological model and constitutive model, you can end up by getting some results that actually match with the actual fail zone as I'm indicating here in this image. But also by increasing your complexity in your model, you can even get the same slip surface as the actual movement, as indicated by this image on the right. As a second part, in order to see the possible effects of different excavation sequences on reproducing the progressive failure, we vary the bench height, the overall slope angle for the pushbacks, and we establish 5 different cases with different excavation orders and geometries, and we compare the models with the previous obtained result from the calibrated model. So for the different 5 cases, we use the same lithology alteration model with the strain softening and the parameters obtained for the calibrated model, but each case represents different excavation sequences. As you can see, there is like changes in the intensity of the displacements, but also it was possible to see that depending on the excavation sequence, you can accelerate the occurrence of the failure or even decelerate it. Like, for example, in case 5 and case 4. Finally, the main conclusion is that in order to get the best result when you are modeling a progressive failure, and if you are using a back analysis technique, it is quite important to represent the real condition of your geological environment, which means to use complex geological models, but also it is an invitation to invest in better geological models, material testing programs, and additionally, it is also important the excavation sequence in order to accelerate or decelerate or to diminish the effects of failure in your open pit. So thank you. I'm glad to hear any question that you have.
Great, thank you, Andreas. That was interesting. If anybody's got any questions, if you pop them in the Q&A group or in the chat box, then we'll come to them after all the talks are finished. So next up, if James, if you want to get your slides ready. So James is a consultant geophysicist. Oh no, that's the wrong one. Jamie, you're next. Yeah. Jamie is a geotechnical engineer at Aiming, and he's going to be providing us with a presentation about the importance of a well-strategized mining risk assessment. Something I don't know much about either, so I'm quite interested in this.
Yeah, just bear with us 2 seconds.
No problem. Yep, that's clear. Do you want to just move for a slide to make sure it works? I think I can navigate forward.
Are you getting everything, or are you just getting the main slide? I can't.
Just the main slide, but it looks like I can move the slides.
That's only for you, I think, Hayley.
Okay, if you just let me know, I'll move the slide forward then.
Is that working?
No, I don't think so. If you just give me a thumbs up each time you want to move the slide on, I'll do that for you.
Okay.
Sorry, I think that only moves the slide for you, Hayley, because if you click it forward, it doesn't work for anyone else.
Oh. This is the new Teams.
That move forward. Yeah, that's working now, Jamie.
Is that working?
Yeah.
Okay, so I'm Jamie. I've been working in geotechnical consultancy for about 7 years. Graduated with honours in geology and then did a master's in geotechnics. I'm going to just give a brief introduction into mining risk today, why it's important, and the key sources that should be consulted in order to diligently assess mining legacy risk. Just checking, can you see that okay? Yeah, I've not used this before, so is it just coming up with the key slide? Yeah.
Yeah, it's got coal mining legacy on our screens now.
Okay, it's just that I can't see specifically what you're seeing. So from Glasgow, and as my hometown has a long coal mining past. Coal mining's been known in Glasgow and in Paisley since the 12th century. In 1914, there were about 30 mines operating in or within the edge of Glasgow. By 1947, there were 225 collieries in Scotland, which is basically a coal mine or a building associated with it. Now there are none. Due to this extensive mining past, there are a number of risks today associated with legacy mining. And this means that a coal mining risk assessment can normally be required in these areas. The aim of a coal mining risk assessment is basically to identify any coal mining legacy risks and set out a proposed mitigation strategy if mitigation is deemed required following risk assessment, to demonstrate to the local planning authority that the site can basically be made safe and stable for the proposed development. So the coal authority should always be consulted for specific reference of coal mining legacy risks to a site. Key coal mining issues that are normally covered are listed in the PowerPoint slide given. And based on desk study sources, intrusive, non-intrusive investigation undertaken, assessment is undertaken to rank these issues from low through to medium and high risk. And some of these key coal mining issues can cause a number of issues for developments, and some of these can include collapse of relict workings beneath buildings, which can cause damage to building fabrics and infrastructure. You can also get migration of mine gases from old mine workings and mine entries, and this can result in the accumulation of flammable and asphyxiating gases in confined spaces. Or on the opposite foot, you can have consolidation of relict workings, which can cause structural defects in building fabrics as well. So the scope of a good mining risk assessment is to really present a review of your readily available information on ground conditions and mining issues which are relevant to your site, to use that information to identify and assess the risks to your scheme for mining legacy, including any cumulative issues, which would be the combined influence of all your issues together. Also to assess the impact of your scheme on existing mining legacy. So on the back foot, your scheme can also have an impact on the risks that are already there. And finally, to identify any mitigation options, if deemed required, following risk assessment, to identify any mining legacy issues, which can include remedial works. Some key sources of information you can go to is the coal authority database. This can be used to identify coal outcrops, probable workings, and mine entries. You can also use it to identify shallow coal seam outcrops, recorded underground workings, both deep and shallow, and mine entries. You can also use it to gain information related to past shallow coal mining and probable shallow coal mining areas. And lastly, and quite importantly, the coal authority interactive viewer also gives identification of high risk areas. If you find your development is found to be within a high risk area, you'll normally require a coal authority consultant's coal mining report. This can be obtained through Groundshore, normally has an extra cost to the client. You basically will outline your site extent to obtain any pertinent information. The report's split into 5 main sections. Normally look to section 1 and 2 first. Section 1 would outline any past underground mining, any probable unrecorded shallow workings, at shallow depth, including mine entries, abandoned mines, any outcrops, geological faults, fissures, or open cast mines. Section 2 goes in to outline any site investigations that have been undertaken, any remediated sites, any coal mining subsidence, including mine gas or mine water treatment sources. More importantly, should also be looking at past mapping. So the National Library Maps of Scotland have a collection of historical mapping available in Scotland. You've just got to make sure you've got the appropriate licenses for commercial reuse. You can also look to the British Geological Survey to gain information related to superficial bedrock geology and linear features. The BGS also has, geological records, exploratory records that should be obtained and studied to ascertain signs of any coal seams, any zones of non-recovered material, for example, voids, as this is normally indicative of past workings. In particular, you should note the thickness, the depth of the coal, and the depth of the coal seams and voids, as this is useful later down the line to determine which coal seam it corresponds to. The BGS should also be looked at to study any solid geological mapping. So they have a catalogue of solid geology maps that can be studied to ascertain linear features in solid geology. This can be used beside geological cross sections to aid in interpretation. For example, I worked on the East Kilbride electrification scheme for Network Rail. And this comprised about 36 boreholes. These were sunk to gain information relating to the geological conditions beneath the site. And using the historical mapping, this was used to interpret the geological sections by referring back to the mapping. Basically, by using this, we were able to identify from the exploratory holes which coal seam corresponded to each in the geological section by looking at its spatial distribution. The BGS also has 1 to 10,000 scale solid geological maps, and this can be used in further interpretation of coal seam thicknesses. Importantly, generalized vertical section is given in the key, and this should be studied alongside the mapping as it presents indicative depths of coal bands and their thicknesses and their spatial distributions in relation to each other. So one example I'd give is if you think that you would have interpreted the Glasgow splint coal to be beneath your site on your geological section, then you would normally expect the Glasgow virgin coal to be there as well, as it's spatially associated with it. If once you've looked at all these secondary sources, you think further investigation is required, you can undertake intrusive investigation, for example, boreholes, to gain information relating to the solid geology beneath your site. On the East Kilbride electrification projects I worked on, I think I already mentioned, but it's 36 exploratory holes that were sunk. And really this was used to aid the design of station extensions, as well as new overbridges and structures. So using the information we gained, this was plotted against the existing solid geology information superimposed. So on the overlay plan above on the section, this took the existing information from geological maps that I'd mentioned, and this was cross-referenced against the borehole intrusive investigation, geological information to interpret the formations, as well as the coal seams and the faults present. Based on the secondary information and intrusive investigation undertaken, this was used to assess any key coal mining risks that I outlined at the beginning of the presentation. And in the case of the East Kilbride electrification, mitigation measures were recommended for high-risk areas. I would say, importantly, in any coal mining risk assessment, if required, your mitigation strategy should set out and illustrate with plans, especially in the case of mine entries, how coal mining legacy risk will be dealt with to ensure the safety and stability of your development. And basically that's just a quick run through and concludes everything that I had to say on coal mining.
Great, thank you, Jamie. Again, if anyone just pops their questions in the question box, we'll come to these right at the end. So last but not least, we've got James. He's a consultant geophysicist at RSK, and he's going to present to us on the use of seismic surveys to determine engineering and geological properties of subsurface soils. So if you're ready, James, I'll leave you to it.
Great. If I just try clicking through a couple of these slides, can you see it moving?
Yeah, you're good.
Perfect. Great. Thanks, thanks both of you. Thanks, Jamie. That was really interesting. I'm James. I work for RSK as a consultant geophysicist. Did a degree in geophysics from Leeds, an integrated master's degree, and I've got about 4 years of commercial experience since I graduated. This is kind of like a short roadmap of how my presentation is going to go. We're looking at seismic surveys, like a specific type of geophysical survey. I'm just going to go over some theory briefly, and then after that, we're going to move on to a couple of different methods in more detail. Firstly, seismic refraction. Then we're going to have a case study where we look at finding the depth of bedrock using that method. Then secondly, I'm going to go into more detail about borehole seismic, so parallel and cross-hole seismic method. And there's a second case study looking at locating a buried wall using those methods. But before we get into any of this, I'd like to share with you a short thought experiment. Apologies for the horrible stock photo, but just imagine that you're in a room, there's the project manager, and there's 3 people, and the 3 people are, there's an engineer, a geologist, and a geophysicist. And there's a very important question that the project manager needs to have answered. And the answer to that question will be integral to the success or failure of the project. And the question is this: what is 2 + 2? So the engineer is straight in there because he knows the answer. He's straight in there. The answer in his terms is 4.0000 to that exact accuracy. There's no deviation, and he knows exactly what the answer is. The project manager says, oh, okay, that's great, but maybe that's not exactly what I was after. Ask the geologist next, what do you think the answer is to this question, 2 + 2? The geologist says it's probably somewhere between 3 and 5. You know, there's some mitigating factors. It might depend exactly on what you encounter on site. You know, I can't really be sure what the answer is. The project manager is like, okay, that's kind of what I'm after, but not exactly. And then they turn to the geophysicist, ask them, what do you think the answer to this question is? And they sit up straight, they lean in because they know this is their time to shine. They lean in really close to the project manager and they say, well, what would you like the answer to be? And this story just kind of like, sorry if you heard it before, you might have done, but this story just kind of illustrates the kind of attitude towards geophysics. I think among lots of geologists and engineers, they kind of see it as like a black box, kind of like a crystal ball. Geophysicists just kind of gaze into their crystal ball and kind of come up with lots of pretty pictures that, you know, they can kind of make them seem to be anything. And there is this kind of principle of non-uniqueness. Basically means you can have several models that are different, which seem to fit the geophysical data quite well. So we're going to kind of discuss this a little bit as I go through my presentation, but also hopefully I can show you by the end of the presentation that even despite that, that doesn't mean that geophysics doesn't have any use. That actually, with other inputs, especially, and interpreted in the right way, geophysics, despite the kind of non-uniqueness, can still be a very useful method. So firstly, just some theory to get through. So what is a seismic wave? It basically measures the propagation of elastic energy in a material, which will vary depending on the body size and shape. There are 2 main types of seismic waves: P wave and S wave. P wave is faster. It's the also known as compressional wave. I like to think of it as like a push-pull wave, P wave, almost like a slinky, you know, like the wave going up and down a slinky. That's more like a P wave. S wave is slower, shear wave or secondary wave, and that's kind of more like if you're like shaking bedclothes with someone else, you know, and you're like trying to get your bed duvet on, shaking it, the kind of waves that go up and down the bed. That's what an S wave is like. There are also surface waves, which we're not going to discuss really today. They're the kind of waves that actually kind of follow on, almost kind of like the ground roll. So like in an earthquake, these are the waves that kind of come after the PNS wave and actually cause most of the damage. But we're not really going to discuss them too much today. So first type of survey we're going to consider is a seismic refraction survey. So this type of survey is you have receivers called geophones. You lay them out, as you can kind of see in the picture, across the surface. Then you inject seismic energy into the surface. Normally, especially the surveys we do, this is just someone with a hammer, just hitting a shot plate as hard as they can with a hammer. The waves go into the ground. They, if there's different layers of different velocities, they will refract and then come back, and you can receive the time of arrival of the waves at the geophones, and you can use this to work out the seismic velocity, the PNS wave velocity of the subsurface. And one thing to consider here with this type of survey is that you do need to have an increase in velocity with depth, because otherwise the physics won't work for the wave to refract properly. So that is a consideration if you're looking for a velocity inversion, a case where you might have a lower velocity layer beneath a higher velocity layer. This type of survey won't be able to detect that. So moving firstly on to our first case study from the seismic refraction method. In this instance, the client wanted to determine the depth of bedrock along about 190-meter corridor. Unfortunately, they couldn't drill and get like intrusive information along most of the corridor because of ecological issues. So what we did is we carried out PNS wave refraction surveys. So as you can see with the figures here, they had two boreholes that they did drill where they were allowed to drill kind of in the east of the line. And that's where we got our induced information from. But we were trying to work out the depth of the bedrock, extrapolating this towards the west of the survey area. So we've got two examples here. The upper example is basically using like a generic initial model, which basically means you're going to get like a very smooth result. It's not kind of like forcing the data to show anything, but you're basically you do this when you don't really have any assumptions you're making. And this kind of gives you like a quite smooth result. You can see the increase in velocity with depth, and you can kind of see how it matches to the geological kind of sections of the intrusive information we have. Then the below model is a bit different. We basically ran the initial model using a two-layer case. So assuming the model only had two layers, so a fast velocity below and a slow velocity above. And you can see that compared to the upper model, the lower model has a much sharper change, which correlated really well, not as well to the borehole logs, but instead to these colorful logs below, which are SPT N values. So the N value, like red in this case, is high N value, blues and greens are lower N values, and that's basically just a measure of like strength of the rock. So interestingly, both of these models had a error value of less than 5%. And that's kind of how we measure in geophys and seismic surveys, like how good your data fits to your model. So even though these models do show slightly different things, they both have an error value of less than 5%. So if we move on to the interpretation of these two models, basically what we gave to the client is two kind of separate interpretations. One, the upper interpretation kind of correlating the data to like a two-layer model with like a very simplistic kind of correlation to those CPT N values from using our two-layer initial model. And the lower one, we have the more smooth tomographic model, but correlating specific velocities we've picked out to the specific layers you found in the borehole models. And we actually presented both of these to the client in the report. And the interesting thing is that neither, you could say, are right or wrong, because we're looking for the depth of bedrock, but it's not like a clearly defined change. It's more of a gradational change when you have this kind of weathered bedrock. And you can see, interestingly, in both of these sections that the bedrock does shallow towards the west of the survey line. So even though it's like maybe not exactly like a clear change that you might expect, like we might have expected this two-layer case to correlate well with the borehole logs, but it doesn't. Instead, it correlates better with the CPT N values. But in both cases, we're showing that the bedrock shallows towards the west of the survey line, and also providing a useful result for the client to try and find the depth of the bedrock, despite this kind of non-uniqueness of both methods. So moving on now to a different type of seismic survey, borehole seismic survey. So I'm just going to go through the theory. The first kind of theory I'm going to go through is something called a parallel seismic survey. This is often used to find the depth to the bottom of a pile. So basically you drill a borehole like right next to a pile, and then you'll drill the borehole to a depth deeper than you think the pile goes. Then you would like strike the top of the pile, the seismic wave will travel through the pile, and at where you get a kind of change in slope, change in velocity, you can see on the right here. That's basically because the wave will travel a very fast velocity through the pile, but when it travels through the natural ground, it will travel at a slower velocity. So you can see where the change in slope comes in. That's basically, you have to correct it using a little bit of maths, but it basically is quite an indicator of how deep the pile is. Another type of seismic survey is a cross-hole seismic survey. This is a little bit different. This is where you have two boreholes that are drilled into the ground, and you'll put your receivers, which basically measure the travel time of a seismic wave, into one borehole, and you'll put your source into the other borehole, which fires. So instead of hitting a hammer on the surface, you have a source that goes down the hole and fires seismic waves like from within the borehole. And you'll basically use the source at lots of different levels and the receivers at lots of different levels in both the boreholes, then swap them around. And using lots of different travel times, you'll basically infer the seismic velocity of the subsurface. And because you've got lots of different ray paths, as you can see here in this section, you can quite accurately kind of infer exactly what the seismic velocity is. So the case study I'm going to show you now is using both of these methods kind of to find a buried seawall. So this was at a port. This schematic shows it quite well. A very, very old wall built kind of in like the 19th century. The one on the left, this was kind of in situ, and where you could see it kind of like in a bank, but you couldn't quite see the bottom of it. It was at like kind of at the base of a channel. And on the right, where the two boreholes you can see in green, they were the two boreholes that were drilled either side of where we knew the wall was, even though it had been knocked down at the top. And basically, the challenge was to find the base of depth of the wall, because they wanted to install cables beneath the wall, and they wanted to know how deep it was, so how deep this buried obstruction was. And they wanted to know that so they could put in cables below the wall, so they would directional drill and not have to drill into the wall. So we used kind of a combination of both the methods that I introduced before. This is the first processing we did, a very simple processing of the data, where the source in one hole and the receiver in another hole, and basically at each meter, just working out what the seismic velocity is. And as you can see, there's quite a clear shape. We also, the two lines shown here are with the source in one hole, the receiver in the other hole, and then when they're swapped around. So that gives quite a nice kind of like error bounds on your data. So as you can see, that they're quite good agreement between the two holes. And also you can kind of see how the velocity steps out after about, 10 meters, 11 meters, it steps out and it gets faster and faster and faster. And then after about 50 and 60 meters, it gets a lot slower. That's indicative of like a fast velocity buried obstruction, pretty much what you would expect for a buried wall. But then we also tried a different processing method. We saw that some of the data with the source down the hole was looking like this, like very similar to a parallel seismic survey, even though we weren't directly hitting the top of the wall because it wasn't exposed. If I just move on to the next slide, actually, what was happening was from the shallow cross-hole data, the seismic energy was traveling through the wall, and then you're getting this change in slope where you have a bottom, like the base of the buried object, and then below where the buried object is, you're getting a change in velocity, because below where the bottom of the wall is, the seismic waves are traveling through more of the natural ground compared to more of the buried obstruction. So even though we didn't kind of intend to do this kind of survey, it was really interesting how the data kind of showed us like a clear change in velocity at a very similar kind of depth, and that was indicative of where the bottom of this buried obstruction might be. And finally, we did a tomography, which is kind of what I showed you with that cross illumination, where you have lots and lots of sources and receivers in both of the holes. And this showed a really clear kind of pattern of kind of the stepping out of this high velocity. So in this plot, red is very high seismic velocity, blues and greens are low seismic velocity. So this kind of stepping out of a very high velocity zone, which you could see in these plots, and then below about 16 or 17 meters, again, like the reduction in seismic velocity back to what you might expect from the natural ground. So again, kind of indicative of this buried obstruction. So just showing these three together, just an interesting case where you've got the three different interpretations, ways of processing the same data set, and all of them kind of showing pretty similar results. Again, it's not exactly clear what might be happening at 16 to 18 meters depth. Potentially it could be the wall has some foundations which aren't quite, you know, as big as the actual mass of the bottom of the wall, which is why you see faster velocities, but not as fast as during the body of the wall. So it's a bit difficult to say exactly where the base of the wall is, but you do have a very good correlation between these three methods, which show roughly where you have fast seismic velocity, indicative of a buried obstruction, kind of tapering off towards about 17 to 18 meters, and below that you likely have natural ground. So quite a successful case study in determining where the bottom of this big buried obstruction was. So just to conclude now, so yeah, just my final points are, hopefully I've shown you that a couple of different ways in which seismic surveys can be used to provide helpful information which can help address geotechnical challenges. Hopefully also in what I've discussed, kind of you can see that results can be complicated. The principle of non-uniqueness means it's not always easy to know exactly which of your models could be the correct one, but sometimes taking these together can also provide a very useful information despite that. And yeah, that your seismic survey, your geophysics should always be used in conjunction with as much other information that you have to constrain it, to provide a good interpretation and to provide a useful result. So there you go. That's my presentation. Thank you.
Thank you. That was really good.
It's a really good presentation.
Nice. I like your little analogy at the beginning. I've not heard that before. Very good. Okay, so we got some questions now. Hannah, have you gone through them, or do you want me to just?
So we've got a few for Andres for his first talk. One from Josh. Andres, not sure if you mentioned this at the beginning, but did you manage to visit the quarry that you were doing your research on?
I didn't mention it, but I couldn't visit the place because it's so difficult to get to the area. So many permissions from the mine operator, and most of the information that it was used for this study, it was secondary information.
Okay, and then a question from Haley as well. What were the main limitations of the model that you used?
Okay, there are several limitations. Like, for example, if you use the more Coulomb constitutive model, there is like a tendency of this model of over exaggerate the tension resistance, which means that the triggering point when it's developed the failure, it could be not assessed properly, which means there are a lot of uncertainty about the failure timing. Another one, it could be the mesh. If you change the mesh, it's probably that the results are gonna change as well. Yeah, I think these two are the biggest limitations of the modeling process.
Thank you. And thank you also just for dialing in from Colombia. And then we've got a couple for Jamie for talk 2. Are there any unusual terms or labels on old maps that might be indicative of coal mining activity?
Yeah, that's a good one actually. The old maps have legend keys, and I wouldn't be able to tell you off the top of my head of one, but there are legend keys provided with the historical mapping, and you could consult that if there was anything sticking out off the top of my head. I I can't give you one.
No
I
problem.
imagine there's some regional differences, is there, as well? I imagine maps in Scotland are probably slightly different to some of the ones in England and stuff. They're probably different terms.
Yeah.
And then we've had a couple of questions relating to using geophysics. If you wouldn't be able to recommend doing intrusive boreholes, how reliable would geophysics be to detect the coal minings?
Oh, this one. Is that one for me or one for James?
Yeah, no, yeah.
Overlapping. Would
Uh,
you like to go first, Jamie?
yeah, so like you can go down for my project Network Rail, we're quite picky about wanting to have a very thorough investigation, but my one understanding of it is you can have a multi-phased approach where you have the boreholes spaced out spatially, but you also have the geophysics that is used alongside it to basically almost work alongside it, and one backs up the other, and that way you're getting hands-on sort of the strata, but you're also using the geophysics to back up over a wider area. That's kind of my thinking on it, but I'm sure James has more elaborate.
Yeah.
Yeah,
No, I definitely agree.
I
definitely agree. Yeah, we do a lot of work finding like relic mine working. Sometimes you're just looking for like shafts and adits. Sometimes you're looking like, I'm doing a project later this week actually where we're looking for like the actual thickness of the coal seam. That's using resistivity, a different method, not seismics. So yeah, we do it all the time, and it definitely works best if you have those intrusive locations, those borehole data to go alongside it, and then geophys can kind of fill in the gaps where you don't have intrusive data, kind of fill in the gaps between where you do have it. And it definitely works best if you have those intrusive locations to constrain the geophysical data and then kind of use geophys alongside it. So yeah, I agree with Jamie.
Thanks, Jamie, and thanks, James. And then James, we've got a couple on yours as well. One from Josh: assuming the boreholes are cased during the seismic crosshole surveys, does the casing affect the results in any way?
Yes, great question. Great question. So there's kind of a couple of ways you can do a crosshole survey. So you need the boreholes to be full of water. So if they're not full of water, you've got to top them up so they are full of water. Often you use a kind of receiver that clamps to the outside of the borehole, so you kind of have to like actually pump it up when it's down the hole. And if you've got a good clamp onto the casing of the borehole, then that's fine. Then the seismic energy can travel through the casing into the natural ground, and then also you clamp the receiver. There is a different type of receiver you can use as well, which isn't clamped, which we use for that survey, the case study I did, called a hydrophone. So basically it's like a geophone, but just works in water. So it senses the vibrations kind of in water. So it doesn't need to be clamped to the outside of the borehole, but as long as the borehole's full of water, again, the seismic wave can travel through the casings, through the water, and you can sense it. But yeah, that's a good question.
And then also one from Haley: what materials are typically high velocity and what are typically low velocity? Yeah,
good question again. So high velocity, yeah, anything like kind of natural, like, like buried obstructions are typically quite high velocity. Bedrock is also, high velocity. It generally correlates quite well to like, as I said, like CPT-N values, or like riffability might be another measure that you can correlate quite well to PNS wave seismic velocities. Shear modulus, like a higher shear modulus correlates very well with S wave velocities, not so well with P wave. So basically just like bedrock, harder materials, high velocity is the general rule of thumb. Like wet, kind of like clay or like superficials, and the wetter they are, like the slower velocity they're going to be, basically. So
fab. Thanks. And then one from Sam Cook: I have a client who loves geophys surveys. I'm more skeptical. I'm more of a trial pit man myself. I think Josh is also a trial pit man now. The task at hand is to find the lateral extent of a former landfill. Would seismic surveys work to locate the edges of former landfill to target some more specific GI?
Great question again. I would not recommend a seismic survey in this instance, but I would recommend geophys. I'd recommend ERT, electrical resistivity, and also EM, because landfill, often the leachate in the landfill, right, is going to be like very conductive compared to the natural ground. It's going to be more resistive. So the contrast you're looking for is that change in conductivity, and the resistivity and the conductivity survey will find that very well. So again, like I wouldn't say like don't do any intrusives, definitely like use your geophysics alongside intrusive data, but a buried landfill, we've done these surveys before as well. It's a great use of resistivity and conductivity, because normally you have a very good contrast between the conductive material in the landfill and the resistive material not in the landfill. So I would still recommend geophysics. Yeah.
Fab. And then another, is it possible to do electrical resistivity tomography and ground penetrating radar?
Yes, it is. They're very different methods. GPR is the one that everyone kind of knows. It doesn't see very deep normally, especially in the UK, especially in clay. Clay ruins everything. So you're not going to see more than 4 or 5 meters, even if you use a very low frequency radar generally, as a rule of thumb in the UK. Normally you use GPR to find very shallow things such as utilities, or like shallow kind of discrete obstructions. ERT can see a lot deeper. So say, for example, you had an ERT line that was 150 meters long, you might see 30 meters deep maybe. So obviously it's kind of like a bit of a different technique. Having said that, I did do a job about a month ago where we used ERT and GPR on the same job. We were looking for leakage, like water leakage through like a canal embankment. So we used like a deep GPR and also used the ERT because they were both sensitive to that kind of like, you know, conductive like water leakage. So you can use them together. Yeah.
Perfect. And then one last one also for you, James. You're very popular. In terms of conducting a sustainable GI, are certain geophys techniques more sustainable than others, or are they all fairly similar?
That's a good question. That is a good question. I think, to be honest, like probably the least sustainable method we do is the method that I presented for the buried wall, because you have to run a petrol generator to actually generate the P wave source. So you've got to leave the petrol generator running all day, because that's how you get the power to generate the P wave, like down the hole. So that's probably one of the least sustainable methods, to be honest, like especially per day. The most sustainable is probably, yeah, something like ground penetrating radar. To be honest, most of the other methods are pretty sustainable because they're not really requiring some of our stuff, like it runs off like car batteries, but mostly apart from, you know, using the generator, I would say our techniques are pretty sustainable. Yeah, good question. I hadn't really thought about that. Interesting.
There's one more, Hannah, I think that you missed as well, from Dave further down.
What's that? Sorry, apologies, Dave. Yes, apologies. Jamie, one for you. Are some areas sterilised by high risk mine risk, i.e. no development would be allowed by risk or planners, or can most risks be overcome by engineering solutions?
Yeah, that's a good one, actually. I think that would touch on mitigations, and that's something that I've not been involved with as much. So yeah, that's maybe one that I can't answer, but one that I can definitely go away and think about.
Thank you. And if that's everything, I'll pass back to you, Hayley. Thank you.
Great. Well, I hope that was informative for everybody. I think it was fascinating. 3 completely different talks and different industries. Well, same industry, but different sectors. So it's really good. If anybody would like to provide any feedback, it is the first time we run this event, so it would be appreciated. And also, if any other listeners fancy giving presentations in this kind of format, then kind of contact us. There's some links on our LinkedIn page on how to contact us. So if you fancy it, then give us a poke and we'll see if we can organise something again if people find it useful. So definitely. And thank you again for everybody, the 3 presenters, because it takes some guts to sit up there and talk in front of people you don't know. So well done. But yeah, we'll leave it there. Thank you, everybody.
Thanks for coming, everyone. Thanks for presenting,
Thank
guys.
you,
Cheers.
everyone.
Thank you very much.
Have a good evening.
Thank you very much.
Have a nice day.
Bye.
Bye.